Hi everyone, we're going to talk about flight. And when we think of flight, we think of Bernoulli, but we also think of Leonardo da Vinci. And you're probably going, isn't da Vinci an artist? Yeah, but he was also kind of this Renaissance guy that invented more things than you can imagine, some of which have actually obviously proven to be correct. He lived from 1452 to 1519, and he was really interested in a practical solution to achieving flight. He watched birds. In fact, he took cross sections and he looked at how a wings was shaped. He invented and figured out the first practical parachute, and a whole bunch of other mechanical devices that he does get credit for. But as he studied the structure of the wing, he really started to understand more about how this could work. And so he actually designed a human powered ornithopter, or a wing flapping device intended to fly almost like a helicopter. So, as we look at that wing, we take it a little farther and we look at something called an airfoil and the evolution of trying to get to that point. And what we figured out is that as you look at this, if I have just a straight board, think of it that way, air is going to move slowly front and back. Basically, as this comes through, all these air particles here want to come back together and just go back to where they were. They're kind of, think of their inertia. And so what happens is that splits, it goes through and the air moves apart and comes back together. But if I go here, you notice instead of going straight, do you see how this has to go up and over? And on the bottom, up and over. And because of that, that air that's here wants to split apart and end up coming back together on the other once the wing goes through. But it has to move a much greater distance than that straight line. And because of that, the air has to move quickly. And the faster it goes, the less pressure it experiences. So if we take a combination of the two, we start to have the ability to get flight. So this slower moving air here on the bottom just has to go straight. Divides, spreads apart, comes back together over here. But here, look how much farther this has to travel than the air on the bottom. And because of that, it has to move fast. And faster moving air exerts less pressure. And because of that, this fast moving air exerting less pressure exerts less pressure down than the air at the bottom pushing up. So if I took this glass of water and I had a piece of cellophane, I could actually flip it upside over and keep this from falling out. Okay, so I'm not going to dump this whole glass upside down, but I can take this bottle, right? And let me make this a little bigger for a moment. And I just have a little bit of water just in case this doesn't work, but it should. And this is just a thing from my HomePod. If I put this on top of it and flip it over, do you see the water doesn't fall out? Because atmospheric pressure, remember, is pushing up at 14.7 pounds per square inch up, and that is not 14 pounds of water. In fact, yeah, there we go. I knew that would be a little bit of a problem, but that's okay. In my classroom, before we had Chromebooks, I would actually take some wine glasses that we have because it had a stem, and we would do this with old overhead projector cellophane, which you may or may not know what that is, and we would literally hang them up over the pods of the desks, and they'd stay there for weeks until I got bored with them. I had one teacher that had one up in his classroom for basically years. Atmospheric pressure is really powerful, and so differences in pressure, once you start to play with it here, can create quite a bit of lift, enough lift to raise an airplane into the sky. So as we go through, now think about this. We have a sneeze. We would expect that gravity is going to pull it down, and it does. Gravity will eventually pull those particles down when you sneeze. But fast moving streams of fluid, and air is a fluid, actually end up going out so fast in this direction that it creates, that fast moving stream creates low pressure. So every air all the way around it is pushing in on that from all directions with 14.7 pounds per square inch, which means, ladies and gentlemen, if you're in the classroom and you sneeze, your particles, if you don't cover your sneeze, will be at the back of the room in less than 2 seconds. And in this age now, post-COVID, that we know about it, we start to appreciate exactly how big a deal that is, because when we sneeze, those particles can go, because a fast moving stream of fluid, um, well, has consequences, even in a sneeze. That's why if you sing, you project more, and because you're forcing the air out more and quicker, it creates a even lower pressure. So when people sing, your air gets farther and farther away much faster and faster. So as we look at this, now I need to make me just a little bit smaller again. We have low pressure on the top because it's curved, and higher pressure on the bottom, pushing that wing up. If we went the other way and we had like an air spoil on a car, where you've got the flat part on top and the curve on the bottom, this would be the faster moving air. So this is my low pressure, and the flat part has the higher pressure. So on a car, an air spoiler actually pushes the car down, and the faster you go, the more forces it pushes down to keep your wheels on the road. And all of this was figured out by a guy called Bernoulli, and hence the name Bernoulli's principle, which basically goes on to say the faster the air flows, the less pressure it has. When air is moving, it creates areas of high pressure and areas of low pressure. The air must reach the end of the wing at the same time, so that the air goes over the top of the wing, has a longer distance to travel, so it has to travel faster. And because it travels faster, it creates low pressure. And I want you to try something. So pause the video when I'm done explaining this, and you're going to go get a spoon. And ironically, I'm recording this in my basement, and the only spoon I could find down here was, well, my spoon from when I was a little kid, which is Mickey Mouse. So I'm not plugging Disney, but it's what I've got. And you're going to hold it like this, just really lightly at the top so it can still wiggle. And let's say that my glass of water is your fast moving stream of fluid. In other words, you're going to go to your faucet and you are going to turn it on, and that's going to become a fast moving stream of fluid, and everything around that fluid is going to be moving so fast it's going to create low pressure, and all the air is going to rush in at 14.7 pounds per square inch. And what you're going to do is, with the curved side facing away from the stream of fluid, you're going to hold it really close to the stream of fluid. And if you're patient and you don't try it, you don't have to push it, it will create enough difference in pressure that spoon will act as a scoop, and it will actually get sucked into your stream of fluid, in this case your faucet being turned on. So try that. It's an easy one to try at home, and it's a really good example of Bernoulli's principle that fast moving streams of fluid create lower pressure and everything rushes in around it. Normally in the classroom I have these really long tubes, but, well, let's face it, in the age of COVID, blowing into a balloon that goes everywhere is not probably the safest thing to do. So, but I'm going to talk about it. So if I have this, it's, I want to say it's like 6 feet long. It's about, in a circle, it's about this big around. And we'd have a competition to see who could inflate it faster. Well, first of all, I always have to disinfect it between hours. I have a bunch of different ones, and then I sterilize them, and then we get used for year to year. But the kids take guesses on how long it will take them to inflate this. And then they try for a little bit, and then they get tired because it takes a long time, because they try and blow it up like a balloon. And I say, well, I think I can do it in one. And they just laugh at me. But what you do is you have somebody hold the end, not open, just away from you. And you take the end and open it. And if, even back here, I were to blow through that tube, my breath creates a low enough stream, a fast enough stream that's low enough in pressure that all the air around it rushes in behind it, and it will fill up that 6-foot bag to at least 4 to 5 feet. And so it doesn't take that much to actually experience how this works. I don't have one of those bags here right now. I'm sorry, I wish I did. But I'm sure if you YouTube it, you'll find something. So the faster the fluid moves, the less pressure it's created. So basically, faster moving fluid creates lower and lower pressure. That's what that's saying. So here we go. Airfoil. Since the pressure is higher at the bottom because it's pretty short distance, it's not moving that fast, this has to move a greater distance to come back together on this side. The top creates high pressure, and we get lift. So once we get lift, We can also, by adjusting the angle of attack or how steep or flat out that airfoil is, we can adjust its speed or its lift. So there's differences there. Old perfume bottles. Have you ever seen this? Where you take the bulb and, it's a lot of times in cartoons. Well, all that was Bernoulli's principle. There is a tube in here, and this squeeze bulb literally just shoots air over the top of this open tube, like a straw, into the bottom, and it creates low enough pressure at the top of the tube that it actually pulls up the perfume, and then it sprays out in a mist with the air from that bulb. And you can do the same thing with a straw. In fact, normally, again, we would do this in class, but COVID, not a good idea. If you take a straw and you're home and you know you're COVID safe and you probably go outside so you don't spew water everywhere, you fill up a glass with water. Cut a straw in 2 pieces. So you got about this big and that big. Put one in the glass. You got to hold the glass and hold the straw. And then you take the other straw and you put just set at the tip of this, and you blow across it. You will actually create low enough pressure that the air in here on the surface of the water will actually push down and push water up the straw until it's expelled and it gets aerosolized out from your breath. Again, COVID, no, not happening. But you can do the same thing if you take the straw and you're playing with it at a restaurant, which I wouldn't recommend. You put your finger on the top of the straw and you lift it out, liquid's still in the straw, then you lift your finger off the top and it all falls out. That's just playing with pressure. It's the same thing as when I flipped that water bottle upside down. This does work. It takes a little bit of practice to get it to work, but it's just basically creating an atomizer, like a perfume bottle, where you're taking and drawing that liquid up. Because remember, on the surface of this liquid, this is the same thing that happens when you actually just drink a milkshake through a straw. It's pretty thick. So if let's say you were drinking pop through a straw or water, what you're doing is you're actually evacuating the air in your mouth, creating lower pressure inside your mouth than in the atmosphere. And just like here, atmospheric pressure pushes down on this surface and pushes it up through the straw. So actually, technically, you're not sucking it in. Atmosphere is pushing it down through the surface, up through the straw into your mouth, because you created a difference in pressure. Less pressure down, more pressure up, you get lift. So here is a good test question. Ready? I have a airfoil here. It's kind of a low, sleeker design. It's going to move faster, but it's going to have less lift. If I increase that curve a lot, it's going to move slower, but I'm going to have a lot more lift. So when we first take a plane off, we want to have this more exaggerated curve because you don't take off at 500 miles an hour or 300 miles an hour. You take off from 0 and you have to gain speed, right? So it's going to be slower, but creating more lift, therefore getting you off the ground. Then once you get to the height you want to get to, then they taper back the wings, and they'll flatten them out so now they can fly faster because they don't need to go up anymore. They're at their cruising altitude, and they will fly faster with less lift. Bigger curve, more lift, and slower. So to slow down, they can actually change the shape of the wing and change the angle. So probably a pretty good indicator that this is going to be a test question if I'm showing this to you in the notes. Now, always just remember, these notes are available down at the folder at the bottom. This is your reference material because you're doing this obviously in Edpuzzle. So think this through, and then we'll check. I've got this flatter airfoil. Is it going to have less lift, fast moving? That's the stuff. Is it going to be equal? Is it going to have more lift but slow moving? Well, in this case, this would be my equal, and yours may be in a different order if you choose to do this. This is a slightly shallower curve, which is going to be less lift, but much faster moving. And this exaggerated curve is what we do at takeoff. This has more lift and slow moving. As always, if you need help, you need to ask